Welcome to the 6th lecture of Module 2 of the course called Game Theory and Economics. Before we start this lecture, let me try to briefly recapitulate what we have done so far. We have defined what is a Nash equilibrium, we have given the definition of Nash equilibrium, and so far we have been trying to analyze different situations, different game theoretic situations, and how to apply Nash equilibrium, the idea of Nash equilibrium, and try to find out as to which are the outcomes or which are the actions that will be taken by the players which will be steady state, in the sense that they will be repeated over and over again. And this steady state kind of outcome is something which is the basic crux of Nash equilibrium. They are a kind of social convention. Given the fact that people have been playing a set of actions, they will continue to play that set of actions, because from each individual's point of view, he expects that the other players will continue to play the actions that they have been playing. So, there is no reason for him to do something else, to deviate and do something else, and this is the very idea of Nash equilibrium. The exercise that we were trying to figure out in the previous class was the case of public good game. Here is the exercise once more to refresh our memory. Each of n people chooses whether or not to contribute a fixed amount toward the provision of a public good. The good is provided if and only if at least k people contribute, where 2 is less than equal to k, less than equal to n. If it is not provided, contributions are not refunded. Each person ranks outcomes from the best to worst as follows. First, any outcome in which the good is provided and she does not contribute. 2. Any outcome in which the good is provided and she contributes. 3. Any outcome in which the good is not provided and she does not contribute. And 4. Any outcome in which the good is not provided and she contributes. Question is, formulate this situation as a strategic game and find its Nash equilibrium. Before we start to find out the answer to this exercise, let us be clear as to what is a public good. A public good in economics has two characteristics. One is that these goods are what we call non-excludable, which means that nobody can be debarred from using a public good. For example, take the case of a public park. Now, if it is an open public park, nobody can be told to just go off the public park. Everybody has an equal right to go to the public park. So, I cannot exclude anyone from using a public good. Or take the case of a road, a government road. Nobody can be debarred from using that road. So, it is not non-excludable. Another characteristic of a public good is that non-rivalry, and what it means is that if I am using a public good, then I do not come in the way of any other person to use that public good. So, this is another important feature of a public good. Again, take the case of a road. If I am using that road, it is not that anybody else cannot use the road. He or she can obviously use the road, but this is different from a private good, which is not a public good. In case of private good, if I am consuming a private good, nobody else is consuming that. For example, if I am wearing a shirt, then it is obvious that anybody else is not wearing that shirt. So, in a shirt is a good where rivalry is there, whereas a road is a good where rivalry is not there. and so a road is a public good. Now, the very fact that in public goods people cannot be excluded, that creates a problem, because look, when I try to build a public good, I need money. Now, if I need money, I have to collect that money from the users, but if I cannot exclude anyone from using that good, how am I going to say to that person, I cannot allow you to use it unless you pay, because I cannot exclude him, and if I cannot exclude him, then I cannot pose the threat to him that if you do not pay, you will be excluded, because it is not excludable good. So, there is a problem, a very inherent problem in public good, that people cannot be excluded, and if people cannot be excluded, it will be difficult to make them pay. So, that is a problem of provision of public good. Now, this exercise is trying to capture that basic problem of a public good. So, what was the problem? Once again, there were n people, and all of them can use this public good, but to construct this public good, to make it happen, you need k contributions from n, not n people, but k people, where k is greater than equal to 2, less than equal to n. So, all of these people who are agreeing to contribute are going to pay the equal amount of money. So, amount of money, once I have decided that I am going to contribute, the amount of money that I am going to contribute is fixed. And there is a problem, that suppose I do contribute and it so happens that the number of total contributors is less than k. In that case, there is not sufficient amount of money, and if there is not sufficient amount of money, the good will not be produced. But though the good is not being produced, I am not going to get back that money. So, that money is not being refunded. So, there is a problem here, because depending on the total number of people, I may not like to contribute. And not only that, remember, if without me paying there are k contributors, there is no reason why I should contribute, because I am going to use that good anyway. It is a public good, I cannot be excluded. So, there are 4 possibilities. Basically, there are 2 possibilities, but each of these 2 cases can be divided into 2 further cases from any individual's point of view. One is good is provided, and the other is not provided. Now, if the good is provided, again there are 2 cases from any individual's point of view. That individual has contributed and has not contributed. Let us call it A, this is B, and if it is not provided, again the same thing will happen. If the good is not provided, there are 2 possibilities. This individual that I am talking about, and any arbitrary individual, has contributed, or he may not have contributed. So, there are 4 possibilities. Possibility 1, that is provided, the good is provided, will happen only if the number of contributors is equal to k or greater than k. If the number of contributors is less than k, strictly less than k, the good is not going to be provided. And what is the preference? I will always like the B possibility best, that the good is provided, but I have not contributed. So, it is such a case that the number of contributors here is either k or greater than k, but I am not one of them. Here I am free riding, I am not paying any money and using that public good. What is the second best for me? Second best is A, which is that I have contributed and the good is provided. Third best is I have not contributed and the good is not provided. So, that is D. D is my third best. And last is the worst possible case for me is C, where I have contributed, but it so happens that the number of total contributors is less than k, in which case the good is not provided and my money is gone. I am not going to be refunded. So, it is a total loss for me. So, this is the ordering then B, A, D, C. Question is, what is the set of Nash equilibria in this game? Now, let me introduce another definition here. This definition is the definition of strict Nash equilibrium. If you remember the definition of Nash equilibrium in general, it was that for every individual I, every player I, this must happen. This must happen. That is A star, small a star is a vector. It is like A1 star, A2 star, somewhere here there is AI star, the general term, and AN star is the last term. Now, the idea is that by playing the stars, if everyone plays the stars actions, then individual I is getting this much UI A star. Now, suppose everyone else goes on playing the star actions, that is the Nash equilibrium actions, and the individual I deviates and he plays some other action from his action set. Capital AI is the action set of player I. From that he plays any arbitrary action. Then the Nash equilibrium, the definition of Nash equilibrium is that by playing any other action, he cannot be better off. He can be doing as good as he was doing by playing the Nash equilibrium action. He can be doing worse by playing the other actions, but he cannot be better off. So, that is the definition. In strict Nash equilibrium, what happens is that if I play some other action, not the Nash equilibrium action, but some other action, then I am strictly worse off. Remember, here I am open to the possibility that the player plays some other action and the payoff is just equal to his Nash equilibrium payoff. So, he can deviate and be just as much satisfied as he was in the Nash equilibrium. But in strict Nash equilibrium, if he deviates, he is surely worse off. So, that is the idea. So, how do I write it mathematically? So, A star is strict Nash equilibrium if for each I Now, this is important, two differences are there. First, I am taking the strictly greater than sign, thus not greater than equal to sign. And secondly, I cannot include a I star when I am talking about a I dashed. If you have noticed in this definition of Nash equilibrium, for all a I dashed in capital A I. So, this a I dashed could have been a I star also, in which case there is a equality here. This will turn into an equality, and I do not want to do that. I want to consider only those actions which are not Nash equilibrium action, and so for every action a I dashed in capital A I other than a I star, and for them it must be the case that the person is getting strictly less. This is strictly greater than. Now, what are the examples of strict Nash equilibrium? If you have noticed, in all the games that we have considered so far, the equilibria that we have generated are in fact all strict Nash equilibria. Let us take the case of any case. Let us take the case of prisoner's dilemma, for example. So, this was the structure of prisoner's dilemma game, and we found that there is a single Nash equilibrium at CC. CC is the Nash equilibrium. From CC, given the other player is playing C, if anyone deviates, suppose player 2 deviates, he is getting 0. Now, if since 0 is less than 1, so from player 1's point of view at least, it is a strict Nash equilibrium. And you will see that from players 2 point of view also, if he deviates, he is getting a strictly less than payoff, which means for both of them it is being satisfied, and hence this is a strict Nash equilibrium. What can be an example of a non-strict Nash equilibrium? Let me give you the example. Suppose this is the game, this is the payoff matrix. There are two players. Player 1 has 2 actions and player 2 has 3 actions. What is the Nash equilibrium here? If we examine the game carefully, we shall see that there is a single Nash equilibrium, which is at TL. This is a Nash equilibrium because if player 2 is playing L, player 1 by playing B is not better off, okay, but he is not worse off either, because he is getting 1 in T by playing T. By B he is playing again 1, and in Nash equilibrium we had this sign greater than equal to sign. Similarly, for player 2 also, by deviating from L to M, he is strictly worse off. If he deviates from L to R, he is doing just as fine as he was doing by playing L. So, this is a non-strict Nash equilibrium. Because by deviating, it is possible that you are doing just as well as you are doing in the Nash equilibrium. It is not that you are doing strictly worse than you are doing in Nash equilibrium. We are going to consider some other exercises. This is an exercise which is a little difficult from the exercises that we have seen so far. Here the number of actions of each player is more than 2 or 3. There are many actions in fact. Now, if there are many actions, then it will be difficult for construct a payoff matrix and find the Nash equilibrium. Then we have to look for patterns and try to figure out if for different patterns does a Nash equilibrium exist or not. So, here is the question. This is a question about voting. So, as we have said before that in political science, literature of political science also, the tools of game theory are used. So, this is one example in which we can use game theory in political science. Two candidates are there, A and B, they compete in an election. Now, there are n citizens, n number of citizens are there. Out of them, k, small k, support candidate A, and m number of citizens, where m is n minus k, support candidate B. Each citizen decides whether to vote at a cost for the candidate she supports or to abstain. So, there are two actions which are available to any voter. He can decide to vote, and if he votes, he bears a cost, or he may choose to abstain, he may choose not to go to the voting booth at all. So, there is an incentive not to vote, because if you go to vote, you are bearing a cost. A citizen who abstains receives the payoff 2 if the candidate she supports wins, 1 if the candidate she ties for the first place, and 0 if this candidate loses. A citizen who votes receives the payoff 2 minus C, 1 minus C and minus C in these 3 cases, where C is a number between 0 and 1, strictly less than 1, strictly greater than 0. What is the question? There are 3 parts to the question. First part, part A, for k is equal to m is equal to 1, is the game same as any considered so far? So, this is an exercise, again an exercise about Nash equilibrium and how to see how the Nash equilibrium changes as the conditions change. So, this exercise is called choosing a route. Let me write down the exercise first, then we shall try to solve the exercise. So, before we go further, let me draw a diagram to show how the game looks like. There are 2 places, one place is A and the other place is B. And there are 4 people who are thinking of driving down from A to B. Now, there are 2 routes to go from A to B. One passes through X and the other passes through Y. Okay. So, here is how it looks like. Okay. The roads from A to X and from Y to B are both short and narrow. So, this is the first part of the exercise. We shall talk about the second part once we have done the first part. As it is written here, the road from A to X is short and narrow. Therefore, as more cars enter into that road, the time it takes to travel from A to X rises, and these are the numbers that show the time that will be taken by cars if the number of cars goes on rising. 6, 9, 12, 15. Similarly, here 6, 9, 12, 15. So, if there is just a single car to travel from A to X, it will take 6 minutes, but if there are 2 cars, each of them will take 9 minutes, and like that it goes on. From A to Y or X to B, the road is wide, but it is a long road. So, the time that will be taken will be like this. So, this is the game. We have to find out, we have to formulate this situation as a game, proper strategic game, and find out the Nash equilibrium. Now, in a strategic game, we know that we have to specify players. Here 4 people are the players. Right? Actions, choosing routes. It could be between A X B or A Y B, and payoff negative of total travel time. They want to minimize the travel time. Obviously, more time you spend on road, it is worse for you. We have to find out who is choosing what route, and that is the exercise. Now, it can be easily seen that it is not likely that all of the 4 people are choosing A X B, because if all of them choose A X B, then what is the time that each is taking? Time spent by each is what? It is given by 15 plus 22.7, which is 37.7. Now, is this the best thing that they can do? Obviously not, because from this situation, if any one of them goes to the other route, which is the other route? The other route is A Y B. If anyone goes for the other route, he will make the journey in 20 plus 6, 26 seconds, 26 minutes. So, all of them choosing the same route is not the optimal thing to do. Therefore, some will deviate, and my claim is that in Nash equilibrium, two people will travel from travel in A X B route spending how much time? If they travel in the A X B route, then each will be spending 9 plus 20.9, which is 29.9 minutes, and two people will travel in AYB route spending, if the two people travel in the AYB route, then the time that they are going to spend is 30 minutes, right, and that is, I am claiming, is a Nash equilibrium. Why? Because deviation, let us consider deviation. If someone from AXB route, if someone from AXB travels in AYB, then he spends how much time? If he travels in the AYB route, then now there are 3 people in the AYB route, and the total amount of time that is spent is 22 plus 12, which is 34 minutes, more than the time that he was spending in the XB route, which is 29.9 minutes. So, there is no point for anyone traveling in the XB route to switch to the AYB route. Similarly, so this is suboptimal. Similarly, we can show anyone in AYB route will not switch to AXB. So, that is why this is a Nash equilibrium. There is a second part to it, second part. Now, suppose a relatively short wide road is built between x and y. So, here I have a changed situation. We have x as before, we have y, x and y as before, x and y. But what has changed is that between x and y there is now a new road. So, besides a to y, y to b, a to x and x to b, I have a new route between x and y, and the time to travel here is 7, 8, 9, 10. So, it is a wide road. Time for the other routes remain the same, which is basically 6, 9, 12, 15. These are the times. We have to find out what is the Nash equilibrium in this changed situation. And my claim is the following: two persons will take the a x y b route, one each in a x b and a y b. Okay. So, this is my claim. So, how do I prove this? Let us find out if this is the situation, then what is the time that is spent by each person. Those traveling in a x y b, time spent, okay, a x y b. Now, I am proposing that there are two people who are traveling in this route. So, what is the time that they will be spending while traveling? First, when they are going from a to x, there are three people on this part. So, 12 plus 8, and when they are moving from y to b, again there are three people, whereas between x and y there are two people. So, 12 plus 8 plus again 12, which is basically 24 plus 8, 32. So, this is the time that they are spending. What is the time spent by the person traveling in the route a x b? Now, the person who is traveling from a x b, he is spending 12 minutes in the first part, in the second part he is spending a x b, he is spending 20 minutes. So, the total amount of time spent is 32, and the person traveling in the a y b route, time spent in the a y portion he is spending 20, but in the last portion he is spending 12. So, he is spending 32. Right. Now, can someone be better off by switching routes? If these people who are traveling in the AX YB route, if any of them switches the route and let us say takes AYB route, then the total amount of time that he will be spending is how much? It is 21 plus again 12, right, and that is 33, which is more than 32. So, switching to this route AYB route is not profitable. If he switches to the AXB route, then what happens? If he goes to the AXB route, he will be spending 12 plus 20.9, which is 32.9, which is greater than 32. Again, switching the routes is not profitable. Therefore, this is the equilibrium. We can see, we can show the same thing for those people who are traveling in the AXB or AYB route also. Now, the funny thing about this result is that when this XY stretch was not constructed in the original game, each person was taking less time, 30 and 29.9 minutes. But when this route is constructed, apparently it was there to help the travel time, to reduce the travel time, but instead of reducing the travel time, it is increasing the travel time for each, because now each person is taking 32 minutes to travel from A to B, whereas previously when this XY route was not constructed, each was taking either 29.9 minutes or 30 minutes. So, this is a kind of interesting and paradoxical result, that maybe building new roads does not help in reducing the time of travel. So, let me wrap up this lecture by just try to recapitulate what we have done. We have defined one new concept, which is the concept of strict Nash equilibrium. Besides that, we have seen two exercises. In one exercise, there was the provision of public good, where we have seen that in provision of public good, there can be more than one Nash equilibrium if the number of people required to build the public good is less than the total number of people. And we have seen another case, another exercise where the number of actions for each player is quite a large number, it is not 2 or 3. So, that in this case we cannot draw the payoff matrix and find out by comparing what is the Nash equilibrium, what are the Nash equilibrium. We have to look at the pattern of the actions and try to find out if there is a possibility of any existence of Nash equilibrium. Thank you. Give some real life examples wherein the Pareto inferior equilibrium remains a steady state, like the coordination game. So, first let us see what is a coordination game. Coordination game is the following game. I am giving one such example of coordination game. Suppose there are two players and they want to meet each other. They can meet either each other by either going to CP. So, this is like Connaught Place, or suppose they can go to DK, suppose Dhola Kuan. Now, if they go to different places, of course, they cannot meet. So, they have to go to the same place so that they can meet. However, going to the same place does not give the same benefit to both of them. Meeting at CP apparently is beneficial for both of them compared to meeting at Dhola Kuan. So, here there are two Nash equilibrium you can verify. One is at CP CP, the other is at DK DK, right. But here DK DK is an equilibrium which is Pareto inferior, because they are getting 1 1, whereas had they met at CP, they would have got 2 each. Question is, how does it still remain a Nash equilibrium DK DK? And we have several examples in real life where dk remains an equilibrium. One example is the case of QWERTY keyboards. So, every computer, most of the computer keyboards which are used are called QWERTY keyboards, because QWERTY are those letters, those keys which appear on the left hand side on top of the keyboards that we use. But this keyboard is not the most efficient keyboard that can be designed. In fact, this is very uncomfortable for any beginner, because if you remember, S, the letters S, A, E all come on the left hand of the person who is using the keyboard, and most of the people are in fact right hand people. So, this keyboard is not a very efficient keyboard, but nevertheless this has become the steady state keyboard. The reason is that if someone else tries, some manufacturer tries to devise a better keyboard, he may not be able to sell that keyboard, because the customers may not buy that keyboard by just observing a very weird kind of design. So, an inefficient keyboard has remained in the market and people are buying it also. So, this is a kind of decay equilibrium that we are stuck with. Define strict Nash equilibrium, give examples. So, a strict Nash equilibrium is an equilibrium where for all players, for all I, this is the payoff in the equilibrium. If everyone is playing star actions, if I deviates, so this AI belongs to his action set, but this AI is not equal to AI star. If this player deviates from the equilibrium action, he takes AI which is not equal to AI star, then he is strictly worse off, and this should happen for each and every player. This means that in a strict Nash equilibrium, the players are getting payoffs which are best for them given what the other players are doing. If they do something else, they are strictly worse off. What are the examples? The most of the examples that we have gone through are in fact examples of strict Nash equilibrium. Let me just repeat one such example, which is the battle of sexes example. If you remember, this was the structure of the game. This was a Nash equilibrium, this was a Nash equilibrium, and given player wife is playing B, if player H deviates, he gets 0, which is worse than, strictly worse than 2. Similarly, for player 2 also, that is the wife also, if she deviates, she is getting a payoff which is strictly less than 1. But this was not necessary for this to be a Nash equilibrium, it could have been 1 also, but if it is 1, then this is not a strict Nash equilibrium. So, that is the point. So, this is, in this case, both this and this are examples of strict Nash equilibrium.